Alright, so we are going to be working on Thermal Physics 5 today. Thermal Physics 5 it's a shorter lecture technically, but the diagrams that you see are the things that are going to come up the most on the AP exam as far as this unit goes, at least when I look through the different problems. And then the FRQs for thermal physics are quite interesting as far as all the directions that they can go in with them, but we'll save that for a later time. So our learning targets, I can define the internal energy of an ideal gas, and so internal energy we will come to learn is quite different from how you might have thought of the internal energy of a system in mechanics. So we'll make sure that we clarify that for thermodynamics, which puts us into our second learning target here. I can explain work in the context of thermodynamics because we know that work and energy are most certainly related. So, the internal energy of a gas is one of the most fundamental concepts in thermal physics. It tells us quite a lot about the gas itself and how all of the molecules are moving. So we saw, I believe I derived it on whenever dip day was, I think that was Tuesday, that pressure and temperature can be related to the average kinetic energy of the molecules in an ideal gas. And you remember I did that derivation just to show you, like, you do not need the MV, and it tells you exactly how, there's always this idea of things move faster, temperature increases, but no one ever really tells you why, and that's exactly what that explains. So the internal energy of a system is the total kinetic energy, this should say here, sorry. Total kinetic energy of all the molecules. That's so internal energy, very important to know, is the total kinetic energy of all the molecules that are in the sample of gas that we're talking about. So as we talked about before, we know that the internal energy of a singular gas molecule, as we derived on dip day, is this. However, if we want it for all the molecules, because we know that the internal energy is the sum of all the kinetic energies, we could just multiply that by the number of molecules we have. And if you remember, we can actually write this also as 3/2 nRT, depending on which form of the ideal gas law that we actually want. And that's actually, you'll see why that becomes a bit more important here in a second, in case you didn't know the temperature, but you knew the volume and the pressure in the gas. So we will talk about that here shortly. So, but this equation here, U is equal to whether you have the number of molecules or whether you have the moles. Definitely very important to know. So the internal energy of a gas, once again, is going to depend on the temperature and the number of moles in the gas. So if we do have the number of moles in the gas, and this is the one that we're going to use probably most often because we don't always have the number of molecules. So this is saying that any increase in temperature is going to cause an increase in the internal energy of the system, and that should make sense because the internal energy is literally just all of the kinetic energies added up. And so we actually have nRT in this equation, and this was kind of what I was trying to get at before. So we know that nRT is equal to PV, so we can also write this like that. I don't believe this is in the reference table. I'd have to, here, I'll actually pull it up right now. Yeah, so when I look at stuff for thermodynamics, yeah, the only equation that they actually have for here is a different equation that we're going to come across for internal energy. So these are both, once again, this one I already mentioned was not on there. It's literally just this one that you get because our reference table is very helpful. But they do give you the multiple forms of the ideal gas law, so you could probably figure it out from that. But we all know that we want to derive as minimally as possible on the AP exam. So that right there is Mr. Joule, in case you were interested. So the state of any thermodynamic system can actually be described by its internal energy, as we're clearly showing here. So the internal energy of a thermodynamic system can be changed in two ways, and these are going to be really important. You can add heat to the system, or you could do work on the system. So again, heat is Q. And it'll become a bit more apparent. Like I remember I failed to mention the whole Q is equal to MC delta T. I'm not really sure how I did that. But I think that the book that I was working from for all this stuff um, assumes that the people who are taking AP2 have always taken chemistry, and we know in Gananda that is not a good assumption. So, we unfortunately I failed to mention a really important equation that I have the expectation that you can use. So sorry about that. So a really simple example that we could think about in thermodynamics is a quantity of gas that's enclosed in a cylinder that has a movable piston. So this can move up or it can move down, depending on what's actually happening to the gas. Okay? So if you consider the work done by the piston as it pushes down, which would compress the gas, that's what we're going to take a look at first. So let's say that the cylinder has a cross-sectional area A and the pressure that's exerted by the piston is P sub piston. That would mean that the force that's exerted by the piston on the gas, let's call it F, okay, then we could say, okay, if we're trying to take a look at the piston as it's moving down some distance x and pressure stays constant, then work is equal to F delta x in the same way that work is equal to Fd, and this is just d this time. We also know that F is equal to P piston times area here, because we don't actually know the force, but we do know this. And we know that if we take a look here, this is A delta X, so we are able to say that that's just delta V. So work is equal to P delta V. And once again, another very important equation and relationship that is going to come in handy. This is the very confusing thing that you're going to run to an issue with a lot. Is that this is actually this is on your equation sheet. I will say that, but it's on there as this. That it's actually negative work, and that is because what we have calculated here is the work that is done by the piston. This would be the work that is done on the piston. It opposes whatever the piston is trying to do. So it's the work that's actually done on it. I'm telling you right now, that's going to be a nightmare for you. I struggled with it when I first did thermodynamics. I struggle with it now when I was reviewing all this stuff. So just really important to make sure that you're very clearly looking at exerted by or exerted on. And we'll make sure that we go through a couple of these examples and doing both. And I actually have a cool chart that I'll show you here shortly, but I know that we obviously remember every single thing that I ever talked about in AP Physics 1, so if displacement is in the same direction as force, we remember that that's positive work. So if the piston moves down, the gas volume decreases, so the work that is done by the piston is positive. So in the scenario that we talked about, the gas is doing negative work since it's exerting an upward force on the piston while there is a downward displacement. So if instead we had a gas that was pushing up on the piston that was causing expansion instead, the work that is done by the gas on the piston is positive, and therefore as the piston is pushed upward, piston is doing negative work since displacement and force are in opposite directions. So that's another way to think about the negative sign. Remember the flippin' physics guy who moved the book up and down, and depending on which direction the force and displacement were, that's how you knew if it was positive or negative work. So that's another way of thinking about this. It's basically what I'm saying, but with a lot more words as far as like force exerted on versus by the piston. But just to kind of put it out here in words and something that you might remember kind of well. So remember, expansion of a gas means that the volume is going to increase. So the work that is done by the piston on the gas is negative, and the work that is done by the gas on the piston is going to be positive. And everything is completely flipped for contraction. So if the volume is getting smaller, we call that contraction. The work done by the piston on the gas is positive, so it's the piston that is pushing down on the gas, and the work that is done by the gas on the piston is negative because as it gets forced down, it is displaced positive, and that is a negative relationship between force and displacement. So, once again, and I guess I kind of jumped ahead to this already, but I did want to make mention of it in case I forgot. So once again, the work here, work is always defined, work, so W equals work done on a system. So if it's the gas exerted on the piston, that's negative delta P here. I can't remember if there's the disclaimer. Let me check it real quick. Okay, so there's a disclaimer, and I'll actually pull it up to the screen here since it's right on the other page. But there's this disclaimer here that you could see in 2 here, and I'll do it in a different color so it's a little more vibrant. In all situations, positive work is defined as work done on a system. And I don't know, I feel like I've pointed that out before, but I'm hoping that now that you've kind of been through AP physics already, that makes a little bit more sense. So that's really important, especially in this equation here, because like I said, if you flip that negative sign, your answer is going to be totally off. So we just need to make sure that we're aware of that. Okay, move this back elsewhere. Okay, so once again, work stands for the work that's done on a system. This is the work that's done by the piston. If there were a positive change in volume, that's an expansion. During the expansion, the work done is negative, and the work done by the gas on the piston is positive. So once again, just make sure that you're thinking through these before you just jump at whatever problem that you're kind of getting into. So work in thermodynamics, once again, I had said that a lot of the diagrams that you're going to see is P versus V diagrams, and you're going to just see just how apparent that's going to become now. So this relationship, once again, so this W equals negative P delta V, that can be represented on a graph. So the area of any graph in any thermodynamic process, the work that is under the curve on a PV diagram, or I'm sorry, the area under the curve on a PV diagram is going to be equal to the work. So in an expansion, the work done by the piston is negative and the work done by the gas is positive. The gas and the piston do the same amount of work, but one is negative and one is positive. So you just got to keep in mind, so work is equal to area, which is equal to P delta V. So that's just to remind you about expansion and work. And then I have another one here that's reminding you about compression and work. Okay. So in a compression, the work that is done by the piston is positive and the work done by the gas is negative. So once again, work is equal to area, which is equal to P delta V. So my advice is to first calculate the amount of work done and then determine whether it's positive or negative depending on what the problem's actually asking you for. Because they will be equal, but one of them is going to be negative and one of them going to be positive. So system is always going to push outwards. So if you think about a balloon, the gas inside the balloon is a system, and the surroundings always push inward. So in this case, that's the air that's outside of the balloon. Hopefully that this makes sense. It'll probably make more sense when you do some examples with it, but just to tell you the convention of system outward, surroundings inward. Okay. So what would be the work done in the process shown here? So you can clearly see this is an isovolumetric process, and if it's not clear, as pressure increases, volume remains the same. So that means that it's isovolumetric. Temperature and pressure must also be increasing because remember, pressure is directly proportional to temperature. So if pressure is increasing, volume stays the same, temperature also has to be increasing. However, if you look at this, you can say that there is zero work done because there is no area underneath this line here. So we know that work is equal to area, and if area is equal to 0, then there's no work done. You can also look at this from the perspective of this is equal to P delta V, whether it be negative or positive. If V is not changing, then this is 0. So in an isovolumetric process, there is no work done. So when you come to me in class and you say, I was feeling isovolumetric last night, I'll know you didn't do your work. It's probably the worst joke I've ever told. I wish I'd edited that out. Anyway, okay. Alright, so an example problem. So the state of an ideal gas is changed in a closed path from A to X to B to Y to A. So we're trying to figure out during the entire process how much work is done on the gas. And what I'm going to do here, because I want to make sure that you could see this while we're doing it, if I could actually close something. And what I'm going to do is I'm going to open this in a new tab as well, just so you can see what I'm writing down here. Give me 1 second, sorry. I feel like half of this video is just going to be me lagging. Okay. So, I'm going to do, here, I should actually make this one smaller. Okay. So hopefully, I mean, I know you have it on your paper, but I want to have it up here. So I'm going to make this a little bigger so that I can actually write. So when you are doing these problems, my recommendation is that you always do one step at a time. Do not try and look at this as a whole thing. The first thing that you will want to do is lay out in arrows what is which direction the system is actually going in, and it very clearly tells you. But I think that it's also nice to sometimes label, especially when you're first starting out with these problems, just to know that it is going in a counterclockwise direction. Okay, I said counterclockwise. That's clockwise. That's just great. Okay. All right. So from A to X, you first are going to look at what kind of process this is, so you could see from A to X, the pressure is increasing while volume remains the same. So that means that if that's the case, there's no work done from A to X. So A to X equals no work done. And then if we take a look, our next step here is X to B. So X to B, we have a change in volume here. We have that volume is actually doubling. So that means that the gas is expanding, which means that the piston does negative work on the gas, which means that, and I know this is very confusing that I'm saying all these things, that work is equal to P delta V. Because the gas is expanding, so piston does negative work on the gas, which means gas is doing positive work. The important thing is, remember, it's the work that is defined as being done on the gas. So since that is negative, this is negative here. Gosh, I can't write. Sorry, it's clearly too late for my brain. Negative P delta V, and hopefully that makes sense. So if I look here, like I said, pressure is doubling, so I can pull out, so if I also need to look at what my pressure is at that point, and it is 2P, so that's another thing that you need to take into consideration. The volume, the pressure was not just P there. So then your change in volume is V minus 2V, so you're going to end up with negative 2PV. B to Y is another easy one. B to Y is also isovolumetric, so from B to Y there is no work done. And then from Y to A, this is a contraction because volume is getting smaller, which means that there is positive work that is done by the piston. So we could say, okay, then work is equal to P delta V. So we have 2V minus V, and I was actually, hang on, I'm being really inconsistent here with this. Let me write that as how it should be. This should be negative P delta V, which is going to be negative P, because that's the value of our pressure there, times V minus 2V, and that will give you PV. This should be the other way around, sorry. I'm struggling. No, that was right. And normally when I mess up, I just start the whole thing over, but I'm in way too deep here, so not going to do that. Final minus initial. That's how delta goes. Okay, so this is PV. Hopefully you can see that here. The negative is going to cancel with the negative there. And then if I look again from A to X, which is just closing the process, there is, or no, we're not even looking at that last step. So no, we're finishing at the point that we started at. So I have 0 plus negative 2PV plus 0 plus PV. So the total work done is equal to negative PV. It should make sense that this ended up being negative, because from at this pressure here, the piston is going to do more work at X to B, since the pressure is greater, because work and pressure are directly related to each other. So, for a thermodynamic cycle, you have to start and end in the same place, otherwise the internal energy would not be conserved. And the net work that is done inside of the cycle, the net work done is the area that is inside of this cycle, okay? So in a clockwise cycle, more negative work is done on the gas than positive work, and therefore the net work is going to be negative. In a counterclockwise cycle, more positive work is going to be done on the gas here than negative work, and therefore the net work is positive. So that's just worth noting as well. So we could do a couple of questions here now. So the temperature of a monatomic ideal gas is increased from 35 degrees Celsius to 70 degrees Celsius. How will its internal energy change? Hopefully you're able to realize that it will slightly increase. Remember that temperature has to be in Kelvin. So this is really, here goes my math again. This is really 308 Kelvin to, oh boy, 343 Kelvin. Why is math so hard for me lately? So this is only a slight increase in temperature, so hopefully that makes sense. The state of an ideal gas is changed through the closed path 1 to 2 to 3 to 1. So what happens to the internal energy of the gas between points 2 and 3? So if I look at 2 to 3, and I look at what kind of graph that resembles, so that I can figure out what kind of process it is, I could say that from 2 to 3, that is an isothermal process. So in an isothermal process, internal energy will not change. So isothermal means that delta Y or delta U equals 0, and that's important to note. And we will get to that a lot. I believe it's in the next lecture that I kind of summarize all of these rules for you. Look, yeah, it is. So we'll get there eventually. You will have all the rules like in a nice little table for you. But so isothermal means that internal energy change in internal energy is 0, and therefore it should remain constant. Okay. Same chart that we're looking at here. The state of an ideal gas is changed in this same closed path. Which of the following is true about the work that is done on the gas from between point 1 and point 2? So I'm looking at point 1 and I'm looking at point 2, and I can say, okay, this is an isovolumetric process, which means that there's no change in volume, which means there is no work that is done by the gas. If volume's not changing, no work is going to be done. So same thing again. If I take a look at this, Uh, we are taking a look at which of the following is true about the work done by the gas between 2 and 3. So if you look between 2 and 3, you can say that work is going to be equal to this area here underneath that curve, and that's a positive value, so that means that the work done by the gas is positive. Um, this is essentially so the volume is increasing along an isotherm, so I can determine that work is going to be positive. We have a new diagram here, so the state of an ideal gas is changed along this closed path. It's the diagram we used before, so it's the diagram we're going back to. And what is the total amount of work that is done by the gas? So this is different from what we asked before. What we asked before was the work that is done on the gas. So what's really nice is that you've already solved for the work done on the gas. So the work done by the gas should just be the negative of that, which is this. And I would encourage you to go through and see if you do get that answer, to make sure that you are actually understanding what's going on here, because I know that this is a lot. So with that, I am going to end this notes and move on to the next one so that we can keep getting through thermo together.